So I'm going to show you how to do the method of joints, method. So I'm using question number 2 from a practice exam that we were given, and I think this is a perfect one because this, it has diagonals in it, and it's not a 45, so it's good to work with. So here are the reactions. First you solve for the reactions. I've already done that just to save time. I'm not going to explain everything here. I'm just going to, quickly run through this. Some of the forces in the x is 0. You have 10 to the right, so that means ax is going to be 10 to the left. Now here it's drawn to the right because you always assume positive when you're solving. You always assume positive. Now that means right or up, depending on your direction. So then I took the moment at A right here, so that eliminates 2 forces. So we have all these forces over here are creating positive rotation, as you can see, because they all want to rotate positively about A, except for EY that wants to rotate negative. So that's the negative right here. And once you sum it up and move EY to the next side and divide by 24 meters, so that's your total. You divide that, the units cancel out, and you're left with 98.75 kilonewtons going up. So that's what this value is right here, and we can actually add that in right now. Kilonewtons, alrighty. And then these ones are also, this is actually going down, this is actually going to the left, so they're both opposites. And you can check that because you have 98.75 going up. You have these forces here that add up to 90 going down, therefore this must be negative 8.75 to create equilibrium in the y direction. Now using our data over here, I'll now jump into the main meat where people are having problems, and I'll address issues such as where to start and how to figure out the diagonals, etc. So that's what I've heard from my fellow students that they're having trouble with. And I'll show you how to figure everything out. It's quite easy. So let us go ahead and add on the information that we've acquired, the information that we've acquired and the information that we were given. So let's start with the info that we're given. So at point B, there's a force going right here of 10. Now I'm not going to bother writing down kilonewton, but just mind you that it's all in kilonewton. At C, we have a 20 going down. At F, we have a 30 going down. At D, we have a 40 going down. Now we found our EY to be 98.75 going up, and we found this to be going down 8.75, and we found this to be going to the left 10. Also, one issue that I'm also going to address is zero members. Now, unfortunately, this is an example that does not have zero members. But for example, if this roller wasn't here, then this member would be 0 because these would take the load instead. But I suppose I'll just do another video for a 0 member one. So where do you start? Now that we've put in all the information we've had, you can't start here obviously because you have 2 unknowns and then you don't even know what these are. You can't start here, excuse me, because you have 3 unknowns. The places you can start is, you can start at D because you only have one known and one unknown in the Y. Actually, I forgot to add these in here. What these lines are just my forces without direction yet. You can start at E because you have one going up. You can't really do anything in for the X. You can start at A because you have one down and then you have one over here, which is probably gonna be up to balance it out. So yeah, the best way to start, in my opinion, is to draw it out according to your drawing. So draw it in a way that represents your drawing, just an exploded version of it, as you can see. It looks like that. If you were to connect all these, it would look like that, just bigger. And what I usually like to do is just to work around it. So for example, here we have 40 down. Now to balance this segment here, to make this segment equal 0, it's quite easy. So we have 40 down. What makes 40 down equal 0? Well, 40 up. Therefore, that's 40. Now, how do we find the x component of it? That is this. Well, we can use ratios or similar triangles to figure that out. It's quite simple, really. So we know that our height is 9 meters, and we know that each of these 3 sections is 12 meters per piece. So 12, 24, 36 in total. So here's how we can set that up. So we have 9 going up and 12 going across. Therefore, we have our 40 here. So we have 40 up, and we'd like to find out our x. So that's a simple ratio that we set up. So we can say that x over 12 is equal to 40 over 9. Therefore, x is equal to 40 times 12 divided by 9. And let us calculate that right now. So 40 times 12 divided by 9. Now, careful with rounding. In this case, you can just use 53. I'm going to use 2 decimal places since we have 2 decimal places here. So we're going to use 53.33. So that is what it is. Now, it's logical that if you're going up and on a diagonal, this part must be going left, because when you add these up, they're going to go in that direction, which makes sense. So we have to the left, we have, even though there's no sign here that says it's a negative, you just have to rationalize that. So 53.33. Now that makes sense. Now how do we balance it in the x? We have 53 to the left, therefore there's one unknown. We can say that we have 53.33 to the right. Alright, so moving on, we can transfer this information here and here. We'll transfer it to the left first. So we have 53.33 going to the right. For this segment, we're going to have it going to the left. It's always the opposite when you jump to the next joint. Remember that. Okay? So we have to the right, therefore we're going to have to the left 53.33. Alright, now how do we balance this? So we can already solve this right away. We can say that we have 53.33 to the right. So that balances it in the x. Now to balance this in the y, we can say that we have 98.75 going down, because we have 98.75 going up. So this is in equilibrium, this is in equilibrium, so this checks out and this checks out. Now we transfer this information over here, and also this we can transfer over here. So let's take the 40. We have 40 up, next joint, it's going to be the opposite. We have 40 down, and 53.33 to the right. And then over here, we transfer this up. So we have, going up, we have 98.75. Now we have one unknown, and we can solve it. And also, we can transfer this over here, if we'd like to. But let's just finish this, because we can solve this. We have one unknown in the y. We have 3 of these. So how we go about solving that? Okay, so we have, let's see, we have 20 going down, 40 going down. That's 60 down, and 98.75 up. So let's do the math. So 98.75 minus 60 is 38.75. So that means we have to add another 38.75 going down for this to be in equilibrium. There you go, 38.75. Now we can once again use our ratio to find the x, and that's going to be going left, because only then can you say that it's going in this direction. So we just do 38.75. What is it? Multiplied by 12 divided by 9. That gives us 51. See, this is where you have to be careful with rounding. You have a 7 there. Therefore, when you're rounding it, you should probably do 51.67 just to be safe, because I'll show you. You'll probably see why that will be soon. Okay, so you have that much and that much. Now, let me just pull out my already pre-done example, just to make sure that I'm doing it right. I don't want to give you guys the wrong idea here. Okay. So okay. So this is done almost. We have one more in the Y here, so let's see. We have 53.33 going right minus 51.67. So that's 1.66 that we have to add going left to equal the right side. Or not the right side, but the force is going right. Now hopefully this makes sense so far. So far D is in equilibrium, E is in equilibrium, C is in equilibrium. I like to check it off when you're done. It's equilibrium means equal to 0, or no acceleration. So this is equal to 0, this is equal to 0, 0. Now what you're going for is a perfect 0, not a 0.0001. And this is a perfect 0. We add these up, perfect 0. We add these up, perfect 0, and I can prove it to you. We have that's a negative, so we're just going to multiply that by -1. Okay, so that's a negative because it's going left, minus 51.67. Okay, and then you go, see, we have negative 53.33 that's going to the left when we have that going to the right, so that's equal to, that's 0 in the x, and then we have 0 in the y also, as you can see that we figured out before. Now we're going to transfer this information to the next two joins. So moving further left to B, we have this, so that's going to be 1.66 like such, and transferring this here, we're going to have 51.67 here, and we're going to have 38.75 there. We transferred that, we have to transfer this too, that's going right, so it's going to be going left, so we have 53.33, and that's pretty much it. Now we can solve for the x here and the y here. So how are we going to do that? Okay, so we have 38.75 going up, 30 going down. Well, the difference there is 8. So we need 8 going down to match this. And you're going to see how that works out. So you can already tell it's relating to this. So we need 8.75 here. So this and this is equal to that. Now let's find out what this is. So that's going to be 53.33 minus 51.67. Yeah, so that's going to be 1.66 going right, because that adds up to that. Okay, hopefully you see how this is working out. I'm just going to zoom in just a little bit. There we go, just so you guys can see much clearer what's going on. Just make this a little bit more bolded. Okay, so this is an equilibrium check. Now we can transfer this up here. So that's going down. This one is going to be going up. So 8.75. Alright, perfecto. So now we can actually solve for this. We have 8.75 going up. Therefore, we must have 8.75 going down here. And this is going down, so this is going to be also going to the left, because that's what creates this this direction. Now to solve for this, we have one unknown and then two knowns. I mean, we don't even have to use a calculator. We can just look at it. Look, we have 11.66 going to the right, so we're going to have 11.66 going to the left. So that's 8.75 here, going down, and that makes sense because this cancels out. And then we have 11.66. Now to balance out the x, we need to add another 1.66 going to the left, and that makes sense because we can transfer this over, and it works. Everything here is equal to 0. This is a perfect system that is in equilibrium, and you can see that. So that's how you do it. Now, so again, there's no particular place to start. It's best to start where you have information that's easy to work with. You can already find out this one, for example, because you have a force there. So if anything, it's best to start where you're given forces, or you found your forces, such as your reactions. And it is best to start where there are the least amount of variables that you have to work with. Now, sorry, not variables, components. So like this one, you have one y and one y here, and you can use this and the ratios to find out the x. And again, setting up your ratios is very simple. It's easy. Most of the time you're not given angles. In fact, we have never been given angles, but this is how you use it to find out your ratios. Now if you had to find out your x component, it would be the same setup. Again, this is just similar triangles. It's very basic math. Now let's go back to our original thing right over here. I'm just gonna zoom in just so everyone can see. Alrighty, so let's add our information back. So I'm just gonna use red. So we have in this force we have 1.66. Now that is tension. Now, okay, now one more thing I'd like to explain. I'll just use this example right here. Is what is tension and what is compression? Tension is when you're pulling away from a joint. So this right here is tension. So this is tension right here, which means that this member would be feeling tension, a pull. And you know it's compression when you have your joint and there's a force going into it. That is compression. It's being compressed. So think of it like that. Okay? So now we have 1.66 kilonewtons. Of course, I'm not going to write kilonewtons because I don't have enough space. That is pushing towards us, so that is compression. In this member, we have 53.33, and that is pushing into it, so that is also compression. Here we have 53.33, same number. That's also compression. At the top we have 1.66. That is pulling away, so that is tension. Here it is pulling away, yeah. Now we have to do a little Pythagorean theorem actually right here to find out the force that's going like that. So we have to do 40 to the power of 2 plus 53.33 to the power of 2. Now mind you, this is rounded, so it's not going to be accurate, but that's fine. So that's about 66.66. So that is about 66.66, and that is pulling away, so that is tension. Here we have to do that again, so 8.75 to the power of 2 plus 11.66 to the power of 2 is equal to that. Take the root of the answer, that's 14.58, why not? 14.58, that's pulling away, so that's also tension. These ligaments, this is pushing in, so this is 8.75 compression. This is pushing in, so this is 98.75 compression. And last but not least, we're going to calculate quickly the diagonal member, 38.75 to the power of 2 plus 51.67 to the power of 2. Take the root of the answer, that's 64.58. So 64.58. And it's pulling away, so that's tension. So just remember, if let's say this is your joint, and you have this is compression. That should be, sorry. So if it's pushing you in, this is compression. Compression. If you have something like this, that's tension. Now the direction is irrelevant, it's just the action that's being performed. So if it's pushing in on the joint, it's compression. If it's pulling away, it is tension. Now that is this fully solved solution. This is how it would look like when you're done. Of course, it's better to redraw this, but I didn't have enough space and enough time, so this is what it's gonna look like, and it makes sense. You know, you're pushing, your main forces are going in a direction like this. You know, you have all this force pushing down, and then you have this one pushing this way. So it's kind of like almost wanting to like rotate like that, if anything, which makes sense why this force is gonna want to pull down, so it brings it back down. That makes sense, because this is kind of like a teeter-totter, if anything. So that's that. Hopefully that addresses on the issue of where to start. Sorry, the issue of where to start, and how to solve for the diagonals. Now, to recap, where to start, anywhere where it's easiest, where you have the least amount of variables to work with. Like you would not want to start at D, or sorry, C. You would not want to start at B or F. It's best to start at places like A, E. Here, I'll just use the blue pen. It's best to start at places like A, D, or even E. Like if you start at E, you can transfer your information over to C. That's not going to do much. It's best to start at your points where your reactions are, and where you have an easy number of X and Y components to work with. Hopefully that addresses all the issues that you've had. If not, please let me know, and I'll try to make another video explaining it. And I will make one that involves 0 truss members. Thank you.